Hi, this is Kelly from Essex Ham and welcome to Foundation Online, getting you started with amateur radio.
Hello, my name's Pete and I'll be your guide for this module. This video is a part of our Foundation Online course. If you're looking to get your first amateur radio license, our free courses can help you on your way with our unique mix of online lessons, videos, quizzes and mock tests, all designed to help you prepare for your exam. We've now had over 10,000 people take our course, so why not join us? The video you're about to watch is a part of that course. It's our quick revision guide that runs through some of the more challenging topics. This video isn't designed to cover the entire syllabus, just the points that you might need to brush up on before your exam. If you're looking for a full set of videos covering the entire Foundation syllabus, please consider signing up to our free course. To book yourself a place and get started, go to www.hamtrain.co.uk. Let's get started with a look at licence conditions and operating procedures. A reminder of the rules for UK amateur radio. Amateur radio is for leisure purposes only and not to be used for any commercial purposes, including business use or advertising. You must only communicate with other amateur radio stations. You must not use amateur radio for broadcasting, that is sending messages for general reception. And you'll need to remember Ofcom's rights to inspect, modify or close down your station, revoke your licence or mandate that you log your transmissions. You'll need to be familiar with the amateur radio call signs. A reminder for Foundation, that's currently M7. For intermediate, we are currently using the 20 series, however this will soon be phased out for the M8 series. And for full, the current call sign is M0. A reminder, you're required to give your call sign as frequently as practicable. You'll need to make sure your station is clearly identifiable at all times. Remember to give your call sign when you're calling CQ, you're changing frequencies, or you're making contact with another amateur. Looking at call signs, you'll need to be familiar with the RSL, the Regional Secondary Locators. Now, in most cases, these are optional, but you still need to know these for the exam. So for England, it's the letter E. You're only required to give this when using an intermediate call sign, for example 2E0 ABC. At all other times, you don't need the E, although it is optional. Most people in England don't use the E, so they would just transmit as M7 ABC. However, the E is optional. For Scotland, the regional secondary locator is M, and you can remember this as names beginning with MC or MUC are being very common in Scotland. An example, MM7 ABC. For Wales, the letter is W, for example MW7. Northern Ireland, it's an I, MI7. For the Isle of Man, it's D, the letter D being the capital of Douglas, the capital of the Isle of Man. For Jersey, it's J, for example MJ7. And for Guernsey, it's the second letter of Guernsey, being a U, example MU7. A reminder, these are completely optional and they can be used to indicate where you're transmitting from. They're only mandatory for the 2 series for intermediate call signs. A common question for the Foundation exam relates to the EMF assessment. This is designed to protect members of the general public from exposure to electromagnetic fields over specified limits. This applies to transmitted power levels of over 10 watts EIRP, that's 6.1 watts ERP. There is an online calculator to help you calculate your safe distances, and you're required to keep a copy of your EMF assessment. Moving on to the Foundation schedule. The schedule is a part of your licence. A copy is provided in the exam booklet. You'll need to be aware of the primary and secondary locations, which you'll find in columns 2 and 3. And remember to watch the exceptions. For example, 431 to 432 Charing Cross. Some frequencies have an ERP restriction. and there are some frequencies that have a limit of just 1 watt. You're also given the band plan in the exam. This includes the 2 metre band and the 20 metre band. You'll note here that telegraphy, or Morse code, typically is at the top of each band plan, followed by data modes and then the voice modes. On the screen now is the 2 metre band plan, and you'll see some exceptions highlighted. 144.4 is where the propagation beacons live. Then you've got the repeater input frequencies and the repeater output frequencies, more on those later, and also some exceptions for the space frequencies, i.e. the International Space Station. The schedule and the band plan are both given to you in the exam in the 4-page booklet. It's well worth getting yourself a copy now. You can download and print out a copy and get used to how things are laid out and some of the terminology. I mentioned repeaters a few minutes ago. Repeaters use 2 frequencies, one for transmit and one for receive, and there is an offset between the 2 frequencies. When accessing a repeater, you need to make sure you're sending the correct CTCSS tones. Next, a quick look at digital voice. In the UK at the moment there are 3 main formats, all competing with each other. There's D-Star, C4FM, which is also known as Fusion, and DMR. The systems generally aren't compatible with each other, which is a bit of a nuisance, but that's the way it goes, and you do need special radio equipment to work each digital mode. Pictured on the screen here is a TYT handheld, which is used for DMR. DV radios, or digital radios, usually have the call sign embedded into the radio software, so if you're lending your equipment to someone else, make sure they're not transmitting your call sign. Let's look now at technical basics. For the foundation exam, you're expected to learn your units. V for voltage, sometimes referred to as potential difference. I is for current, measured in amps. P is for power, measured in watts. And R is resistance, which is measured in ohms. In a circuit, the current is the flow of electrons. Good conductors of current include copper and brass, whilst insulators, which don't allow the flow of electricity, include wood, rubber, glass, plastics and ceramics. You also need to know the difference between DC, direct current, and AC, alternating current. Batteries are usually direct current, DC, and in the UK our mains electricity is AC, alternating current. Next, the first of the 2 formulas that you need to know for foundation. The first one is the power formula. This helps you calculate watts. The formula is power equals voltage times current. In the exam, you're frequently given 2 values and expected to work out the third value. The easiest way of remembering this is with the use of the triangle, which you can see on the screen now. A handy tip here is just to simply remember the triangle, P at the top and then V and I in the bottom corners. If you can hold that in your head till the exam, and then perhaps scribble down the letters PVI on your exam paper, that may well help you. To use the triangle, you have to know what you're being asked for. So if you're asked to calculate the watts in power, what you do is you put your thumb over the letter P. What you're left with is V times I. If you're told to calculate the voltage, then again you put your thumb over the letter V for volts, and you're left with P, the power, over I, the current. P over I. To calculate the current, again, your finger goes over the I, and you're left with P over V. P divided by V, the power divided by the volts. Once you get used to it, it's fairly straightforward. The second formula is called Ohm's law, and that states that the voltage is equal to the current times the resistance. Again, one more triangle, V, I, R. V at the top, then I and R down the bottom. To calculate the volts, thumb goes over the V, and you're left with I times R. If you want the resistance, your thumb goes over the R, and you're left with V over I. And to calculate the current, or I, thumb over the I, and you're left with V over R. Now one of the more challenging parts that you might need to know about in the technical basics section of the exam, series and parallel circuits. Pictured on the screen is a basic circuit in series and in parallel. We have a battery and two light bulbs known as lamps. For the in-series diagram, the current passes through one lamp and then the other. The current that's passing through the lamps is the same. Here you can see I've drawn the voltage. The voltage required for the circuit is the sum of the individual voltages through each lamp. So if the lamps require 1.5 volts each to light, the battery will need to be 3 volts, 1.5 plus 1.5. Compare that with in parallel. Here the current passes through both lamps at the same time. The same voltage, also known as potential difference, passes through both lamps. So here, if the lamp requires 1.5 volts to light, you can get away with a 1.5 volt battery. The current required is the sum of the current through each lamp. I do understand that this is not an easy concept, especially if you're not familiar with electronics. To try to help explain this a little better, it might help to think of electric current like water. On the screen here you can see the same drawing but done in two different ways. We have current flowing through the battery, into two lamps in parallel, back to the battery. The current flowing through the circuit is 4 amps. At the point where the circuit splits and the current then flows through two lamps in parallel, the current going through each lamp is 2 amps. Imagine this like water flowing through a pipe. Water flows downward through a pipe and gets to a join, where half goes down one pipe and half goes down the other before joining up to a single pipe at the end. Half of the water will take one path and half will take the other. If you're just not getting the hang of circuits in series and parallel, the good news is there should only be one question in the exam on it, so if you're really not getting the concept, there's no need to worry too much. There are some frequencies you're expected to remember for foundation. The mains frequency is 50 Hz. Remember, the frequency is alternating, and it alternates 50 times a second, 50 Hz. You're also expected to remember two audio frequencies, AF. The human hearing range. Our ears, in good condition, can cope with signals between 20 Hz right the way up to 15 kHz. And when you're transmitting speech, the bandwidth is between 300 and 3000 Hz. Sorry, no easy way of remembering that. They're just two sets of numbers you have to remember. Then there's the radio frequencies. HF is 3 to 30, VHF 30 to 300, UHF 300 to 3000. Possibly a handy way of remembering this is to think of your VHF radio stations on a domestic VHF radio. So typically you might listen to a radio station between 88 and 108 MHz, Radio 1, Radio 2, Radio 4, etc. That's on the VHF band. So if you can remember 88 MHz, that's between 30 and 300, so in the VHF range. Let's look now at transmitters and receivers. On the screen now is the transmitter block diagram. You can always tell it's the transmitter because it has the symbol for a microphone, not the symbol for a speaker. So going left to right, from the microphone, we go into the audio stage. Box 3 generates the radio frequency that you want to transmit on, and Box 2 mixes your audio from stage 1 and your frequency from stage 3 together into a single radio signal. It's called the modulator. Once you have your radio signal, it's amplified in the power amplifier Box 4 and fed to the antenna. Handy tip here, the audio stage is always by the microphone or the speaker, and the RF stage is always by the antenna. Let's look at the modulations. You have AM. On the screen now at the top, you can see our audio signal, so our speech. Underneath that is the carrier, constant. If you mix the audio and the carrier together, you'll see the waveform going up and down in sync with the audio signal. So we are modulating the carrier by the amplitude, so the height of the wave. The alternative mode is frequency modulation, FM. Again on the screen you can see our audio signal at the top, our constant carrier in the middle, When you mix the two together, you'll see that some of the waves are closer together than others. This means that we have modulated the signal by the frequency of the waves as opposed to the height of the waves. So let's look at that on our transmitter block diagram. You can see the signal coming in from the microphone into the audio stage. Our radio frequency is generated by the frequency generator, the constant waveform there. Mix the two together in the modulator and you have a radio signal. You then amplify it at the RF power amp stage and feed it to the antenna. So let's look at the receiver. The antenna receives all the different radio signals that are out there. Box 1, the tuner and RF amplifier, will find the signal that you're after and amplify it. Number 2 removes the radio frequency, just to leave you with the audio, and number 3 amplifies it for the loudspeaker. Again, remember that the RF stage is by the antenna and the audio stage is by the speaker. And if you see a speaker, it's a receiver, not a transmitter. Looking at that in practice, you can see here the signal received from the antenna goes to the tuning and RF stage. The carrier is removed by the detector, leaving us just the audio signal, which is then amplified and fed to the speaker. A quick look at sidebands. Normally, AM, amplitude modulation, transmits 2 sidebands, but you only really need to send one, and you get better results putting all of your transmitting power into just one of the 2 sidebands. Pictured on the screen here is upper sideband, which is to the right of the carrier. Note that you can have upper sideband or lower sideband. Lower sideband is usually below 10 MHz, and upper sideband is above 10 MHz. A common question we're asked is, why the difference? Well, it's steeped in some amateur radio history and dates back to when there were some technical challenges setting up upper and lower sideband. It later became technically easier to sort this problem out, but the tradition has stuck, and below 10 MHz it's normally lower sideband, and above 10 MHz it's normally upper sideband. One to remember for the exam. The next thing you'll need to know for your exam is the analog to digital conversion process. A to D or D to A is done using a computing device such as a computer or some kind of device with a computer processor built in. An analog to digital converter, ADC, samples analog signals and produces a digital representation of it. You can see on the screen here an analog waveform converting to digital. Going the other way, digital to analog, or DAC, represents a digital signal in analog format. So remember, analog to digital done using a computer, ADC, analog to digital converter, and DAC, digital to analog converter. Staying with block diagrams, here's a relatively new one. This relates to SDRs, or software defined radios. The first image you can see here on the screen shows a receiver. On the left you have the antenna, then the A to D analog to digital converter. Next the digital processor, and then the digital to analog conversion to the loudspeaker. Incoming signals are converted from analog to digital. A mathematical operation done by a computer processor sifts the signals into separate frequency components. The resulting signal is then converted from D to A for the loudspeaker. And below that you'll see the transmitter, where you have a microphone. Your analog voice is converted to digital using the A to D. The signal is digitally processed. Then the D to A, digital to analog, then into the power amplifier and off to the transmitting antenna. Let's look now at feeders and antennas. There are two types of feeder. There's coax cable, which is unbalanced. The signal is in the middle of the cable with a screen on the outside to reduce interference. The other type is ladder line, which is balanced, two equally spaced strands. There are four connectors that you need to know about at foundation. The two large ones are the PL259 and the N-type. These are both screw thread locking. For the smaller connections, there's the BNC, which is a bayonet connector where you push and twist, and the smaller SMA, which is a screw thread. A look now at the different types of antennas. One of the most common ones featured in the exam is the dipole. This is a balanced antenna with two equal halves. A dipole is half a wavelength long, so if you want to work on the 20 metre band, the antenna will be 10 metres long. Next, there's the quarter wave ground plane. This is a vertical antenna that's a quarter of the wavelength long, so for the 2 metre band, it will be 50 centimetres long. Next, the 5/8 wave ground plane. This is 5/8 of a wavelength long and will typically have a coil at the base of the antenna to help with matching. These are typically used on a car where you want your signal to be pushed out to the horizon. Next, the end-fed or long wire antenna. These are unlikely to be of the correct length, so the antenna will need to be matched using an AMU, antenna matching unit. The end-fed or long wire is more likely to cause interference, EMC, than other types of antenna. And the Yagi antenna. This is a directional beam antenna. You'll recognise these on the roof of many houses in the form of a TV aerial. It's basically a dipole with a reflector at the back and several directors to focus the energy into one direction. Yagi antennas have a gain, which is measured in dB. A reminder that at foundation you're required to know about antenna gain and possibly have to calculate it. Fortunately, the table is given to you in the exam booklet. You can see the table here. A gain of 3 dB will double the gain. A gain of 6 dB will multiply it by a factor of 4. 9 dB gain by a factor of 8. And 10 dB by a factor of 10. And the measurement of gain is in decibels, dB, relative to a half-wave dipole. A common question here is how can an unpowered lump of metal double the power? There's no amplifier in there. The easy way of thinking about this is to think of a torch. If you take an ordinary bulb and connect it to a battery, the light shines in all directions. If, however, you put that bulb into a casing and put a hood on it, the energy from that light is focused into a beam, i.e. a torch. If you're a distance away from the torch, you'll see the light shining brightly because it's focused into one direction. The same is true with a Yagi antenna. The energy is focused into a tight beam, meaning it's more efficient and the observer will see more signal than if it was transmitted in every direction. And this is where ERP comes into play. ERP is the effective radiated power, which is measured in watts. So a good example here, an antenna with a gain of 3 dB would double the power. If you were to put your 10 watts at foundation into a Yagi with a gain of 3 dB, you'd actually be sending out 20 watts in the direction of travel. Staying briefly with antennas, a reminder that you're expected to know about polar patterns for the exam. Pictured on the screen here is a half-wave dipole. This one is vertically mounted and you can see that the signals go out in all directions. The picture here on the right shows what the polar pattern would look like in 3 dimensions, effectively like an inflated car inner tube, with the signals going out in all directions towards the horizon. Remember that diagram? You may see it vertically or horizontally in the exam. Looking now at the Yagi polar pattern. Here you can see the radio signal is going in the direction of travel. At the back of the pattern you can see the side lobes. Some signal does go out to the sides and behind the direction of travel. Again, remember the polar pattern for the Yagi and the half-wave dipole as they may appear in the exam. Next, the balun. You use one of these to connect an unbalanced feeder, such as coax, to a balanced antenna, such as a dipole. Remember that, balun, balanced to unbalanced. Next, a quick look at propagation. Radio waves travel in straight lines. Waves can be reflected or diffracted, in other words bent. Radio signals get weaker the further away you get from the transmitter. And the distance you can get depends on a number of factors: the type of antenna you're using, the frequency you're transmitting on, the power, any obstructions between the transmitter and the receiver, and also the conditions. You should also remember that as the frequency increases, the wavelength decreases. A quick look now at VHF and UHF propagation. VHF and UHF is typically just beyond line of sight, so if you can see it, potentially you can work it. The range of VHF and UHF decreases as the frequency increases, so UHF will typically have a lower range than VHF. A look now at HF propagation. This is where you can get your signals around the world. This relies on the ionosphere. Common exam question here, so remember this bit. The ionosphere is a layer of conductive gases between 70 and 400 kilometres above the Earth. If you send an HF signal into the ionosphere, it's refracted or bent back down to the Earth, so it can get a signal around the world. HF bands are either open or closed depending on the time of day and also the time of year. A look now at EMC, Electromagnetic Compatibility. This is all about minimising interference. Typical ways of reducing interference are to move the transmitting aerial away from the thing that you're causing interference to reduce the power, to fit filters, and of course it's good practice to have a good RF earth. On the screen now you can see pictures of 4 different types of filters. We have the clip-on ferrite that goes around your coax cable. We have filters that can be plugged into a TV set to reduce interference. You can also wind your wires around a ferrite ring. And on some mains plugs you'll have a ferrite filter. A quick look at modes and EMC. FM is the least likely to cause interference. Handy way of remembering this: friendly modulation, FM. AM or single sideband are most likely to cause interference, as the amplitude is constantly going up and down. You need to be aware of the danger of high voltage, which is electrocution, the danger of high current, overheating and risk of fire. If you come into contact with a casualty that's suffering from an electric shock, don't touch them until the power is disconnected. Mains plugs, remember your wiring. They need the correct value fuse and make sure they're not damaged. There's a risk of RF burns. Don't touch an antenna while it's transmitting. Take care with ladders, make sure they're secured and somebody at the bottom holding them. And also with antennas, make sure they don't fall off and they don't come into contact with any other cables. Inside the shack, keep things safe, have a clearly marked off switch, and make sure you don't do any work on electrical equipment that you've still got powered on. Other hazards include damage to hearing through headphones and cable trips. So that's it, the end of our quick revision guide. Again, a reminder, this doesn't cover the entire syllabus, just some of the more important topics. This is just one of many videos that make up our free online foundation course. If you found this video useful, please visit our website and sign up for a free place, where you'll get access to all of our videos, printable handouts, and access to our unique collection of quizzes and mock tests, all designed to help you pass your foundation exam. The web address is www.hamtrain.co.uk. Thanks for watching this latest module of our Foundation online course. We hope you found it useful. If you're looking for some more help with your studies, we do recommend the Foundation Study Guide, available from Amazon in Kindle or paperback format. Thanks for watching again, and best of luck with your studies.